In today's videos, we're going to talk about this idea that we call similar triangles. This idea of similar triangles can be difficult at first, but once we know the actual concept itself, then it gets a lot easier. Say, for example, I have this triangle. And this triangle here is a right triangle because that's in 90 degrees. Sometimes when we look at this, we might ask ourselves, is there like another version of this? You could. Let's say I wanted to paste it. It could look something like this. This is identical. But one thing that we can also do is, well, we can enlarge it. Something like this. This is the idea of similar triangles. Notice what I did. All I did is I took the same shape, but what I did on this right side is that I made it larger. That is the idea of similar triangles. They have the same shape, but in reality, they have different sizes. And that's the thing we want to point out. Despite them having the same different sizes, maybe we can use this idea of same shape that we can maybe get some unknowns. What you notice with the same shape is that these things called the angles stay the same. So notice that when I draw this, both the angles are the same. The 90 degrees is still 90 degrees. The angle right here is the same as the angle right here. And the angle above is the same as the one above. That's what it means by same shape. And we can clearly see different sizes. One is clearly larger than the other. So I'll give you an example. This is a famous one called the 5, 12, 13 triangle. And let's just say I doubled it in size. 10, 24, and 26. That's what it means by similar triangles. Notice that when I compare the two sides, they would remain the same. 5 doubles to 10, 12 doubles to 24, and 13 doubles to 26. So, if we have something like that, how can we maybe find unknowns? Let me draw another triangle. Say, for instance, I drew this triangle right here, and I labeled it as, 3, 5, and 7. Obviously, this is not a realistic triangle, but we'll just use it for our example. Suppose I just did the same thing where I copied and pasted it, and I just made it a little bit bigger. So I'm going to do that, but I'm going to change the numbers. So in this one, let's just say I did this time 9, 21, but I have this one called x. Well, I have to ask myself, how do I figure out x? What am I doing from 3 to 9, 7 to 21? To this, we use what we call a ratio. A ratio compares two numbers. And so when we look at this, we can just ask ourselves, what can I compare? Well, in both triangles, I compare two sides. Maybe for the first one, the small one, I can compare 3 to 5. While for the big one, maybe I can compare 9 to x. And remember what we talked about, how they have the same shape, different sizes. So because of this, what I'm going to do is I'm going to make them equal to each other. Okay, so I clearly have this fraction, 3 over 5 equals to 9 over x. One of the things that we can do once we have these two ratios is simply cross multiply. So here's how cross multiplication works. All I have to do is just multiply 3 times x, and then I have to do 9 times 5. 9 times 5, that gives me 45, while 3 times x gives me 3x. You make them equal to each other. So you say 3x equals to 45, and you're trying to solve for x. I don't like that 3. So I'm going to divide both sides by 3. 3's cancel out, leaving me with x equals to 15. And that makes sense, right? So if you look at this original triangle, 3 times 3 gives me 9. 5 times 3 gives me 15. And 7 times 3 gives me 21. So this all checks out. And that's the essential idea of similarity. You're kind of just noticing that from one side to the next, you're simply multiplying by some random thing. We call this multiplication the idea of a scale factor. This scale factor is pretty important because it carries out to say in the future, hey, is one triangle similar to another using this idea of scale factor? We'll continue that in the next video.